We're going to talk a little bit more about some properties of acid bases and their equivalent Kas and Kbs. So let's talk about an example of a weak acid that we're familiar with, acetic acid. And we know that acetic acid breaks down, there's an equilibrium between its hydrogen ion and its acetate ion. And this here is our conjugate acid, and this is our conjugate base. Now, interestingly enough, I think I've mentioned this before, but in a weak acid, and I'll mention it again because it's important, the conjugate base is a weak base. Okay? The weaker the acid, the stronger the conjugate base is a base. So our Ka for this reaction was equal to concentration of H plus times the concentration of the conjugate base, acetate, all over the concentration of acetic acid, the acid right there. We know that if we react our acetate, a base is acid. This is our acid up here. So if we react the conjugate base here with water, H2O, liquid plus acetate, you'll get this in another equilibrium where you form the acetic acid. These are related equations. And we'll see how in just a second. So this here is our base, this is our conjugate acid, and that's our conjugate base. So in a weak base, the conjugate acid is an acid, is a weak acid. So what we can do here is we can set up our Kb equation right here. And we can just simply get that as the ratio of the conjugate acid times, that's acetic acid right here, the conjugate acid, OH minus all over the conjugate, the base here. Now, an interesting property, let's do some math here. You can actually see that if you take the conjugate acid, the acid constant, and multiply it by the base constant, Kb, what you get is, you can do some algebra here. We have our Ka here over HCH3COO. That's our Ka right here. Ka. Multiply that by our Kb, which we get here, which is HCH3COO OH minus all over CH3COO minus. You can see we can do a little canceling here. This cancels out, the base cancels out, and the acid cancels out. And what you're left with is Ka times Kb is equal to concentration of H plus times the concentration of OH minus, which is equal to, if you recall, the water constant, which is 1 times 10 to the negative 14. So you can actually, given the Ka or Kb, you can calculate the Kb or Ka of its conjugate acid or conjugate base, respectively. So that's an interesting property. I want to move on to talk a little bit about buffers. And a buffer is a solution of a weak acid or base with its salt components present in solution. And if they're in a similar ratio, these solutions are resistant to pH change. So, like, let's say, for example, if we have a comparable concentration, let's say we have a 1 molar solution of acetic acid. So we have 1 liter of a 1 molar solution of acetic acid, and we add 1 mole of NaCH3COO. So this is what I mean by its salt components. So here we have the acetate ion, which we know is a weak base, mixed in with our solution. So if one adds base to this solution, say a strong base like hydroxide, what that will do is the acid will react with this base, and what you'll form is you'll form the acetate ion, more acetate ion, and water. So it'll neutralize some of that. If one adds if one adds acid to the solution, the conjugate base, acetate in this case, will react with that acid, forming more HCH3COO, aqueous. So we'll ultimately, that's why they call it a buffer, because it'll absorb any extra acid or base to go into solution. So that will resist your pH change. Now, what we can do is we can actually calculate look at we can calculate the pH of a buffer solution if we know the Ka of the acid as well as the molarities of the acid and the conjugate base. And I'll show you briefly how we do that. We know if we have HA, where A is the conjugate base, in aqueous solution, so like the A could be acetate or fluoride or oxalate. Make H plus A minus, aqueous. We know the Ka for this equation is concentration of H plus times the concentration of A minus all over the concentration of HA. Now, what we can do is we can derive the Henderson-Hasselback equation using some simple log properties. We can take the negative log of both sides of these equations. And so the Henderson-Hasselback equation is pH is equal to the pKa plus the log of the ratio of A minus to HA. So for an example of this, how we can apply this is, what is the pH of a 0.10 molar acetic acid solution where the acetate concentration is 0.5 molar. Now we know that the acetate ion is a weak base, so we would expect it to be a little higher than normal. So what we can do is, if we know the Ka of acetic acid, I think I give you this in a former notes, is equal to 1.8 times 10 to the negative fifth. So the pH of this solution is equal to the negative log of the Ka, pKa, times 10 to the negative fifth. That's our Ka. Plus the log of the ratio of the conjugate base, which is 0.5 molar, all to the ratio of the acid molarity, 0.1 molar. And when you can calculate that, we get to a pH of 5.4. So slightly less acidic than a 0.1 molar solution of acetic acid. So you can calculate that too if you like. That's a good review problem. So that's it. That's it for buffers. We'll do a little. We're going to do a POGIL activity on buffers when you guys in class. Make sure you bring your notebooks in that in those worksheets.